Hi there. So welcome back. This is lecture 3 of machine learning from data, and we're going to address this important topic of is learning feasible? And we'll cover why that's a relevant question, and it's a very important question because if it's not feasible, we're done. Quickly, a recap from last time. So last time what we did was we introduced the perceptron learning model, where we derived the perceptron by thinking about how a person would assign credit as a linear combination of features. You compare it to a threshold that gives us the sign of W transpose X. And then we showed that, how to pick, that defined a hypothesis set, an uncountable hypothesis set. How to pick one, you need a criterion. So the criterion was, does the hypothesis look good on the data? And the algorithm was the perceptron learning algorithm. And, we showed that at least computationally, when the data is separable, we can find it. We can find a good separator. Okay, but that doesn't mean that the separator we find, approximates F. It approximates F on the data set. So today, we're specifically going to address this issue of what happens outside the data set. Now, I had a lot of questions asking, you in the learning setup, you forced us to pick the hypothesis set ahead of time. And I'm claiming that this is without loss of generality. And someone pointed out to me, but these commercial machine learning packages and so on and so forth, they ask you to, to present them with the data, then they show you the data, and they show you some statistics of each individual variable, and then you get to pick between, let's say, the perceptron, the linear regression. Do you want to do logistic regression? Do you want to use a polynomial model? Do you want to use a support vector machine? Do you want to use a neural network? So it gives you all this choice, and you pick one. Okay. And the key is it's showing you some data, and then on the basis of that, you sort of pick a model to use, and then it goes and does some automated thing and produces a final hypothesis. So two things. The first thing is that commercial setup is equivalent or can be placed within our framework with the simple realization, with the simple observation that effectively before you saw the data, your fixed hypothesis set was the union of all those things they were showing you. Okay. So think what happens before you look at the data. That commercial software, has the set of options which are, linear model, logistic, polynomial, neural network, support vector machine. So it has all of those. So you collect all of those into one big hypothesis set. Okay. And that's the fixed hypothesis set that you have before you look at the data. Now, it turns out that the learning algorithm they were implementing was something somewhat sophisticated. It had a manual part where you got to pick a sub-hypothesis set based on, exploration of the data. And then it had this automated part where it took the sub-hypothesis set and produced a single hypothesis. No problem. The point we're asking you to do, is to be upfront and to be explicit and just simply say, this is the hypothesis set I'm working with. And it's always the case that there is a hypothesis set you're working with in the background. Okay. And you must be explicit and state it. And then the theory says that sets a boundary for where you can go. You cannot select a final hypothesis outside that boundary. Okay. That's very important. So we're just saying, be explicit, be upfront, tell us what's your hypothesis set. It can be a large hypothesis set like that commercial system, or it can be a small one, like you say, I'm just going to fix it to the perceptron. Okay? But whatever it is, tell us what it is. Then we can do the theory. Okay? Now, one of the things that's, that might lead you to sort of, to realize that, they may not be operating in that realm is that, what do they present you at the end? They present you the final hypothesis and maybe show you how well it does on the data. Okay? And if they're going to show you how well it's going to do outside the data, then it's very dangerous what they did. What they did was to, ask you to pick and then, run a polynomial model and then, see how it does on the data. And then maybe they'll try to figure out, well, what do we expect outside the data? And what we will see in the theory is that, when you're trying to analyze outside the data, you have to go back to the original hypothesis set, which is all the hypotheses. And so if you have to go back to the original hypothesis set, which is all the hypotheses when it's time to see what's going to happen outside the data from the theoretical perspective, you might as well be upfront from the very beginning and state your hypothesis set that defines the boundaries from which you can pick a final hypothesis. Okay. Now, let's talk about is learning feasible. And last time we ended with this fascinating puzzle, where I asked humans, and you were the humans. So you can't say, did you pick the right humans? Did you pick some silly human? I think you guys, unless you think you guys are not the right humans, I picked you guys, and you guys couldn't agree on what the test point is. And there's a very simple reason why you couldn't agree. The simple reason why you couldn't agree is there are many explanations of the data, okay, that will result in this this outside the data point being +1, and there are many examples that are many explanations of the data that will result in -1. So the target function being +1 -1 is equally consistent on the outside data point, is equally consistent with all possible explanations of the data. Okay. And this is one of the things you sort of investigated in one of the exercises. Okay. And if the target function is truly unknown, okay, then how are we going to pin it down outside the data? Because all we have is the data, and the data is equally consistent with the target function being +1 outside the data for this particular point, and also -1 outside the data. Okay. And that's a real dilemma. Okay, so let me summarize. We have a very simple problem, okay, but it got very messy. Humans cannot agree on what is the right value of f outside the data. Okay, and that's because either value of f is equally consistent with the data. Okay, and that's sometimes called no free lunch. Okay, so what now? Okay, this raises the question, if f is truly unknown, is there any hope whatsoever that a finite data set can help us to know anything about f outside the data? If we can truly take on either value outside the data, then how does the data help? So it turns out, and luckily for us, the answer is yes. Okay, but if we're willing to give up the for sure, okay, so we will never know for sure what's going on outside the data. But if we're willing to give up the for sure, if we're willing to live in a world of very high probability, okay, I'm almost certain but not quite sure, then we can, say something about outside the data. So our goal for this lecture is twofold. The first is to see what can we say outside the data, okay, and we're going to reduce the problem from the full learning problem to a much simpler problem, okay? And then we're going to connect that simpler problem to learning and leave it at that for today. Okay? So can we infer something, anything whatsoever, however small, something outside the data using only the data? Okay? And let's go to the board, okay? Because I want to write in order to slow myself down. This is a very important topic. Okay, so let's try to figure out if we can learn something out of the data. This is very important because out of the data is the only thing we care about. So I'm going to go slowly and so try to pay attention. So we're going to simplify the problem and address a much simpler problem in the context of learning, okay, and that's the Gallup poll or sampling. So think, in the November election, we'd like to know who's going to win the election. So what we do, we go out and sample some, potential voters and ask them how are they going to vote. Okay, now we get this sample and we see how many vote for Trump and how many vote for Biden, and then we're going to estimate from this, who's going to win the election. Okay, so let's, build an abstract model of sampling. Okay. And in this abstract model, there's the what's called the population or the collection of voters. We'll just call that a bin. Okay, so you have a bin. Okay, and in this bin, you have two different kinds of voters. So we'll call the voters marbles. So, the people who are voting for Biden, we'll call them the green marbles, and the people who are voting for Trump, we'll call them the red marbles. So in this bin, we have a collection of different colored marbles. Some of them are red, some of them are green. So you've got a bunch of green marbles. Okay, and you've got a bunch of red marbles. So this is an abstract model of the Gallup poll, or it's a model of sampling with replacement to be technically accurate. Okay. Now in this bin, we have, some red and some green. Let us say that the fraction of red marbles is mu. Okay, so mu equals fraction of red marbles. Okay, and just for argument's sake, just to be concrete, let's imagine that it's equal to 0.4. Okay. Now, here's what sampling does. When you sample, you go and randomly pick a sample. Okay, so imagine that each marble has a probability associated with it, and then, we pick a marble according to that probability distribution, and then we replace it. We pick a marble according to that same probability distribution and replace it. So we repeatedly pick marbles. Okay, so that's called sampling. So we sample. And we generate what's called a sample of marbles. Okay. And some of the marbles we generate will be green.
Okay? And some of the marbles we generate will be red. Okay? And in this example, I picked 10 marbles, and 3 of them are red, and 7 of them are green. Okay? Now, we don't know what's going on in the bin. Okay? That's all the people in the USA as an application in the Gallup poll example. Okay? But we know exactly what's going on in the sample. So in the sample, okay, which we can consider to be our data. So this is our data. So in the sample, we know we can compute the fraction of red marbles. Okay. We can certainly compute it because for each member, and that's exactly what the Gallup poll does, for each member of the sample, we are going to ask, who did you vote for? Okay, or who are you going to vote for? Or in this abstract marble, once we pick the marble, we can look at its color. Okay, so we know the color of all these marbles. So let's define the fraction of red marbles in my data as nu. Fraction of red in sample / data. And in this example, just to be concrete, in this example it's 0.3. Okay. Now, important. Nu, I know. So we can call this inside the data. Okay. And it's nice to know that, I sampled 10 people and 3 of them are red, 3 of them are Trump voters. That's nice to know, but that's not really what I want to know. Okay. What I really want to know is who's winning the election, i.e., I want to know the fraction of people in the population who are voting for Trump. I want to know the fraction of red marbles in the bin. I want to know mu. Okay. So nu is inside the data. It's known. Mu is outside the data. Why outside the data? Because to compute mu, I need to know the colors of marbles. In fact, I need to know the colors of all the marbles. I need to know the colors of marbles that are not in my data. So it's related to outside the data. So mu is outside the data. Okay, and it's unknown. Okay, so it's unknown. Okay. And so here's a very simple learning from data problem. Much simpler than, learning an entire target function. Okay. All I would like to know is what is the fraction of red marbles in the bin, which is an outside the data quantity. And all I know, okay, what I know from the data is the fraction of red marbles in the data nu. So the question is, can I reach from my data nu into the bin, mu, somehow, and infer mu? Can I reach from nu to mu? Okay. Now, when we do these Gallup polls, of course, they don't take samples of size 10. Okay. They'll take a sample of size, let's say 1,000, 10,000. So they'll poll about 10,000 people. Okay. Now, is it the case that I could say mu equals nu? So this is what we do when we believe in a Gallup poll. So is it true that mu equals or is approximately equal to, let's say, mu? Okay. And here's the bad news. The bad news is we can never say for sure. In other words, it is always possible. Okay. It is possible for bin to be mostly, let's say, red. So that means mu is approximately equal to 1. Yet, sample is all green. So nu is approximately equal to 0. It is always possible. You just got unlucky. Okay? By chance, when you were picking your sample of size 10, even though most of these guys are red, okay, you happen to pick 10 green marbles. It is always possible. And we can replace 10 with 1,000. It is still always possible. It's just that you're very, very unlucky. And we can replace 1,000 with 100,000. And it is still possible that you pick all 100,000 green. And you are very, 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 very unlucky. And you should not buy a lottery ticket. Okay. But the point is, it is still possible. Okay. So we cannot for sure make any conclusions about mu. Okay. In fact, Okay. Just like our little machine learning problem where, on the data, you can get explanations of the data that are equally consistent with f being +1 versus, explanations that are consistent with f being -1. Mu taking on any value from 0 to 1, okay, but not including 0 and 1. So any sort of non-trivial value between 0 and 1, mu can take on any non-trivial value between 0 and 1 and be consistent with whatever data set you get. Okay, and that was sort of where we left it off with that example, okay, where we were led to this question, is learning feasible? So it looks like it's not possible, okay, to make any conclusions about mu given mu. It's not possible if we want our conclusion to be for sure 100% correct.